everybody coming in. Welcome to now we're back. We're all, I guess, not in the fall, but Insider's Guide to the Galaxy, and we are back on regular schedule. And we are ready for a great episode. Yeah, you know the drill. Say where you're from in the chat. How the weather is, anything cool you've observed lately? Have you observed any new messiers? I was just saying I was in Algonquin in the dark skies. However, it was Saturday night when the moon was full. So it was a beautiful moon, but I couldn't see anything else. I was really hoping to catch the lagoon or Triffid. But
look, even if it's a full moon, just grab the binoculars and scan around and you'll find lots of neat little star patterns and things like that still work.
I always like to still show people the moon too. They're always amazed by it if they're not used to astronomy.
Yeah. I do want to do another tour of a section of the moon in an upcoming session, but looking at the calendar for the rest of this year, there weren't any nice times where the moon is in the right phase the couple of days after our scheduled Insider's Guide, but we'll definitely keep it in mind for after the new year. Still going.
As long as you all stick around and keep wanting to watch us, we'll keep doing this. Or we at least praise Chris a little bit, because he does a lot of good work for this. Okay, so I think we have still people filing in, but we are 2 minutes past the half-hour mark, and let's ready to get started. This week we're going to be talking about variable stars, but because this is such a large topic, this is just part 1. Yeah, I got to come back next week to finish it up.
2 weeks.
With 2 weeks. 2 weeks. And with that, I'm going to pass it off to Chris just to jump right in.
Sit down and do my burgers, and I was reminded about how cool they are and how accessible they are. And but when I finished my notes, I looked at it and I thought, oh, we're not going to get all this done today. So let's breathe a little, slow it down a little, and split it into 2 parts. I think it'll be worth doing it now. And also let us have time for questions. Now, this is a great time of the year to talk about double stars because most of the best and most accessible ones are visible in the nighttime sky, mainly evening, some late night at this time of the year. And then by the time you get up and running, the other, say, 2 or 3 that aren't around now will be available fall time. So you'll be ready to tackle those. I'm going to talk about, double variable stars are stars that vary in brightness. We're going to share some examples of the stars that do that, talk a little bit about why they do that. And then in the next session, we'll get into some of the serious parts about, creating charts that let you measure them numerically, their brightnesses, and submit observations and things like that. So we'll do that. It turns out that in the sky, about 1% of all stars are variable in some fashion. So, there are lots of them out there. And why study them? Well, the American Association of Variable Star Observers, that's a mouthful, AAVSO. I believe their president, if she's still their president, I hope she is Stella Kafka. I love that name, Stella, and I think it's great that a great astronomy name, Stella. They say that research on variable stars is important because it provides information about stellar properties, such as the star's mass, their radius, their luminosity, their temperature, their internal and external structure, their composition, and their evolution. And much of those information sets wouldn't be available if they didn't vary. So we get a lot of the physics about stars because they're doing something that's measurable and noticeable. So we'll start off with a bit of a talk about star brightness. So how we measure or measure star brightness. So obviously we use the term apparent magnitude being the brightness in the sky. And it's brightness because the way something looks, the brightness of something depends on how far away from you it is. So if you take a given light and you bring it right up close to your eyes, it's very, very bright. Then if you take it to a great distance, then it's a lot fainter. So the inherent brightness of an object is called its absolute magnitude. But the brightness or magnitude of objects we see in the sky, we call the apparent magnitude. I hadn't really thought about this before, but the concept of the magnitude scale originated at the time of Claudius Ptolemy back in 170 AD is when he lived. And his idea was to rank the stars by their brightness in the sky. So he put the first rank stars were the brightest ones, and then he had 6 categories. So the stars that were barely visible, he called those rank 6. And so that translates into magnitude 1 to magnitude 6. And that's why the magnitude 1 star is brighter than a magnitude 6 star instead of the other way around. We're used to the number going up and the brightness going up, but it's reversed because it's more the rank rather than the value. In 1856, an astronomer named Norman Pogson, he took that scheme and he formalized it, and he decided to make it so that a magnitude 1 star is 100 times brighter than a magnitude 6 star. And if you do some math, it works out that each integer change in brightness is 2.512 times difference, or 2.5. So the rule of thumb you can remember is that a magnitude 1 star is 2.5 times brighter than a magnitude 2 star. Now the scale for that system is anchored at the star Vega, which is up in the sky in the summertime for us. That's set at magnitude 0.0. And anything brighter than Vega, which of course can be the sun or the moon or other objects, and even though some other stars are brighter than Vega, of course, they get negative magnitude values. So you've got 0 for Vega, you've got +1 to be 2.5 times fainter, and -1 would be 2.5 times brighter. And it just works that way. What we do is we then take a look at these stars and we estimate their brightnesses. And if we compare a star that varies to the stars around it that don't vary in brightness, we track its change over time. And if you take a number of measurements and collect those and remark on their date, the time you saw them, eventually you can plot up a graph that shows, a systematic curve or variation of that star. And it can vary in different ways. It could be sinusoidal, it could be a notch, or it could be a sawtooth. There's different types. Now, the maximum brightness of the star we call the maxima, or the maxima for plural, and the minimum that the star gets, the minimum. And then the cycle time, the time it takes for that to repeat, is the period of the star. So you've got period, maxima, minimum of the star. And we'll get into some more about that a little bit later. So where did this all start? Well, obviously, we have the sort of scientific revolution and the more modern scientific, principles that started publishing papers, recording measurements on things. But really, the observation of the sky goes way back. And there is evidence that perhaps the ancient Egyptians noticed that Algol, the bright star Algol, which was one of the more accessible variable stars, was brightening and dimming in the sky because they produced, we have a surviving papyrus of a document called the Calendar of Lucky and Unlucky Days. And it just varies. It has a number of events that happen over time. And if you analyze the sort of time sequence that's built into that calendar, one of the periods that comes out of it is the same as close to the period of Algol creation, in addition to the moon and other things there. So there's a possibility that they noticed it. I'm sorry. I know that my internet connection's misbehaving today, and I'm not sure why. Also, it's possible that the indigenous sky watchers noticed some of the stars varied in brightness and may have lore around that. I did ask our friend Isaac Murdoch before we get that guide if he knew of any knowledge around that, and I haven't heard back from him yet. But if I do for next time, I'll be sure to share that. Now, the first star to be formally recognized as variable is Omicron Ceti. So I'm going to share my screen to get into Stellarium here. And we'll bring that up. Right. I'm going to bring up some bookmarks. Here we go. Date and time. So the way it worked, the way this went was way back on August 3rd of 1596, an astronomer named David Fabricius was looking at Jupiter. So let's just bring this up. I have to do one more thing first. Click here, click here. Here we go. So here's the sky in 1596, August 3rd, and he was actually looking at a bright planet. He thought it was, I think he thought it was Mercury, but it was really actually Jupiter. They were still getting organized at that point, I guess. And he wanted to note its brightness. So he compared it to a star in the neck of Cetus, the sea monster, the star right here, which is called Omicron Ceti. And so he used that star as his sort of comparison. It was shining at magnitude 3. And 2 weeks later, when he went back to do some more notes about Jupiter, he saw that the star had increased in brightness to magnitude 2, which he noted. And then by the time he got later into the autumn and October timeframe, the star was gone. He couldn't see it at all anymore. And so he thought maybe he had witnessed a nova, so a star that exploded and faded out over time. But actually, he kept logs, and we have his notes. And he reported that it returned to view in February of 1609. So it was back. So there was something weird going on with the star appearing and disappearing. By 1638, an astronomer named Johannes Holwarda, he announced that he had been studying Cetus for a while and worked out that it seemed to reappear and disappear over an 11-month cycle. And Johannes Hevelius, who lived around the the 17th century, he studied the star, and he actually came up with the name Myra. So the proper name for Omicron Ceti is Myra, which means wonderful. Because in 1662, he realized that it was varying as well. Things got more rigorous around 1667 when an astronomer named Ismail Bulialdis, he published a formal period for Myra or Omicron Ceti of 333 days, which is very, very close to the accurate amount. There are hints in the literature that maybe the Chinese noticed that Myra was varying and other things, but nothing too definitive. Okay, so around that, by fast forward a little bit of time, in 1669, we've got another astronomer. His name was Geminiano, and he had been taking a look at Algol. So we mentioned Algol. Let's bring that into view here. So here's Algol. Algol is currently rising eastern sky in the evening time. He noticed that that Algol varies in brightness. Now, Algol in sort of Greek mythology was the demon star. It's the eye of Medusa. So if you look up this depiction of Perseus, these stars in this little group represent the face of the head of Medusa. And obviously the ancients had noticed that Algol varies in brightness. And so they had assigned it to the sort of supernatural, the pulsing red eye of Medusa. So Montanari started to pay closer attention to Algol and recorded that one as a variable star. The next stars to be recorded as brighten as variable were Chi Cygni. So here's Chi Cygni, which is in the neck of the swan. That was recorded. So that one varies from magnitude 3.3 to 14.2, which is basically it vanishes over a period of about 408 days. That was in 1686. And then the star named Arhydri, which varies in a similar way over a bit more than a year. That was announced in 1702. So these were starting to sort of come in thick and fast. By 1786, there were about 10 formally recognized variable stars. An astronomer named John Goodrich, he actually did some more thinking about Algol, and he published an explanation that Algol might be an eclipsing binary star system. So we'll come back to that in a little bit. He also did some work on Sheliak, which is a star down here in Lyra, and Delta Cepheus, another, so Shelliac and Delta Cephei are two other very noticeably varying brightness stars that, that you'll be able to look at yourselves. In about 1786, a gentleman named Edward Pigott, he tabulated then 12 variable stars. The first real catalog of them, though, which contained about 123, that was published in 1864 by George Chambers, and it was called the Astronomische Nachrichten. And things were kind of stable at that point. But around the end of the century, about 1890 or so, photography and photometry kicked into gear, and that let astronomers take photographs of stars and then look at the plates later and note how the stars varied from plate to plate. And that really exploded the number of variable stars in the sky. By 1907, Annie Jump Cannon, who is here at the Harvard University Observatory, she published a catalog of 1,957 variable stars that she had gleaned off looking at the library of photographic plates that the Harvard Observatory have been putting together. So things march on. By the time we get to almost nowadays, as of March 2017, there is something called the General Catalog of Variable Stars, or the GCVF, and it has 52,000 of them in it now. Most of those by far, of course, are in our own Milky Way galaxy, but we're even seeing variable stars now in other galaxies and in the large and small Magellanic Clouds as well, which are in our neighborhood. I think Samantha can pop the link into the chat if you like, of the place that you can find that catalog and some more about it.
Yeah, and I was just gonna jump in before we move on to ask a couple questions we have.
Sure.
Just to clarify, we are having some issues with Chris's internet right now. We apologize. We're hoping it gets better. He's plugged in. He has done the best he can right now. Thank you for letting us know. We have two questions. One is the difference between absolute and visual magnitude. So absolute magnitude of a star is kind of what the magnitude or brightness of the star from a standard distance, which is 10 parsecs away, or 32.6 light year, versus the visual or apparent magnitude is what it appears like when it gets to us on the Earth, or what you're seeing it as. So absolute, if you want to compare the brightness of stars, like just straight up what they are, then you'd use absolute. But visual, we often talked about visual magnitude of what it appears to us when we're observing. There's another question about standard candles, and I don't know if you're going to go a little bit deeper into Cepheid variables later, or.
So we'll probably cover Cepheids next time.
Okay.
That's the
our question about standard candles will come back in 2 weeks, and we'll talk about them a little bit more.
Yeah, we did actually do a previous session of Insider's Guide where we talked about measuring star distances, and we talked about standard candles using Cepheid variables at that time, but I'll go over it again when we come back. Yeah, good questions.
Perfect. And as always, if you have any questions in the YouTube, you can put it in the chat, or we have the Q&A, as well as all the links will be shared in the chat, or if you want to go back and look at them later, they'll be in the YouTube description box of the recording.
Perfect. All right, let me just bring us back to 2022 here. All right, good. So naming double stars. Now, we know that regular star names, the ones we hear about all the time, are these proper names. A lot of them are derived from Arabic phrases. But of course, you know, those are the main stars in the constellation. After you get into the more fainter stars in the constellation, they start getting either, let me just pan around here and find a few more of these. So here's the constellation of Sagitta, the arrow. And you can see that it has one knit star with a proper name, Sham, and it is Alpha Sagittae. So that's generally the brightest star starts with alpha and so on. And then it goes beta, delta, gamma, etc. down the list. When you run out of Greek letters, then you start using the numbers. Now, actually, every star has the number. The numbers run from west to east. So you can see that this is 5 Sagittae as opposed to 7, 12, 13, and they go higher. The numbers go higher as you march across the constellation. Yeah, so you can get these, these letters, Gamma, Eta, and so on in the constellation. Now, the variable stars were the astronomers wanted to give them their own designations. So if a star already had a Latin alphabet designation, they didn't, bother renaming it just because it was variable. But they didn't want to create names to identify the stars that didn't already have designations. So around the early in the 17th century, an astronomer named Friedrich Argelander, he came up with a naming system for variable stars that were strictly for variable stars, and he kept the ones that already had their proper names and their Bayer letters. And what he did was that as of his time, as of his era, as of 1836, only one constellation in the sky had used the letters up to all the way to S, so alphabeted all the way to S. So he decided the variable star should start being named from R onwards, with the capital letter R. He would do R, R, S, T, U, V, all the way to Z. If he still needed more, and by the way, then he would add the constellation's genitive names. So it would be, if you're talking about Lyra, then you'd be talking about R Lyrae or T Lyrae, that kind of thing. So if you're using an app and you see a name like that, then that's a clue for you that that's a variable star in the variable star list. Okay, but what if you more than to the letter Z? You go back to R and you do RR, and you carry on from there. RR, RS, RT, and so on. And if you finish up those to Z, then you come back to S, and you go SS, ST, and so on until you've done all the combos. And by doing that, you can actually fill up 334 of the variable stars in the constellation. Now, that quickly became untenable. More stars started to be discovered. So then we started using the term capital letter V and a numerical number. And since we already had the 334, then we decided that the next variable star we picked up would be V 335 and 36 and so on. Now V, forget
You cut off
5,000 and something. Yeah.
Sorry, we just missed that last part after.
Oh, I said, I think up to now we're up to V 5,000 and something. Yeah. Again, though, that there are kind of more and more stars being discovered, so we needed something even more scientifically rigorous. So the Harvard Observatory proposed that astronomers use a six-digit number composed of the right ascension and declination of the star to designate the variable stars. So if you go into one of the the variable catalogs, the CVS catalog, you'll find that those designations are in. Again, it's a math link in the interested in. Let's go back to Myra here, just get into the evening sky. And again, just stop me if there are any questions as we go. So why do stars vary? Well, they can vary for a number of different reasons. I'm actually not going to cover all the various types. If you go to the variable star Wikipedia page, you'll see some, major types there, and then lots and lots of subtypes. And a lot of those are stars that would not be observable to full. They vary of a magnitude, very too fast. Measure with a telescope and a computer and that sort of thing. So I'm just going to talk about the main primary systems. So the variable stars are divided up into two sort of families. You have intrinsic variable stars, in which the star itself is doing something to vary its brightness. And then you have extrinsic variable stars, in which something is acting on the star's brightness or interfering with the star's output, blocking its light and causing it to vary. Stars can vary in brightness visually in the visual wavelengths, but they can also vary in their spectra, in their color. And I'm not really going to get too deep into that side of things, but I've got only one mention of that as we go. So let's start with talking about the extrinsic variable stars, and then next time around, we can get into the intrinsic variable stars. So the most famous extrinsic variable star that everybody talks about, or that you'll see when you look up the topic, is Algol. And Algol is an eclipsing binary. And what that is it's a star where you've got a pair of stars orbiting one another, and the plane of the orbit is close to line of sight to us, to Earth. And that means that it's possible for one star to pass in front of or behind the companion star. And that varies the total light output that we get from them. I'll show you a light curve for that here. Bring this in. Here we go.
I'll throw the link into the chat where you can see it as well, while Chris pulls that up.
Yeah. So this is the light curve of Algol, otherwise known as Beta Persei. Sorry, Jen, was that Samantha?
It wasn't popping up, but it's up now. We're all good.
Good. So you can see that most of the time, the output of those two stars shines up here at about a little bit brighter than magnitude 3.4. But then on a regular periodic cycle, the light of the output that we see dims dramatically for a period of time. And that is because the stars are lined up one in front of the other. There are points in time where we don't have observations, typically due to it being in conjunction with the sun and that kind of thing. This graph comes from the TESS satellite, the Transiting Exoplanet Survey satellite. And what TESS does is it stares at these stars for a long period of time and takes very careful measurements of their brightness. And then what you can do is take a long series of measurements and then determine the period of regularity, or the repeating cycle of the time series, and stack them together. And when you stack them together, you the noise and any uncertainty in the signal, and you get this nice crisp looking chart. So what I'm going to do is I'm going to bring up the animation of what's going on. I'll show you what I'm talking about. Right. So what you're seeing here on the top, these orange blobs, these are actual photographs of the two stars at different times. And then down below, you're seeing an animation of what's happening. So you're seeing a small companion orbiting in the main star. And these are photographs synchronized to that of the. So what you've got here is an orbital inclination of about 84 degrees. So it's not quite edge onto the Earth. You can see it just sort of misses, but it gets close. So the 26 times less luminous companion, it crosses the main star every 2 days, 20 hours, and 49 minutes. And when that happens, you get that deep V, and the star's brightness drops dramatically. And they call that the minima. So when you read about the minima of Algol, it's the time at which those dips in the light happen, and they list those. I'll talk a bit more about that in a second. So the apparent brightness of Algol drops from 2.1 down to about 3.3 times fainter. And the dip takes 10 hours to go down and up. So 5 hours down, 5 hours up. Generally speaking, it's hard to see the minor dip. So what you're seeing is when the big dip is happening when the faint star is blocking the light from the bright star, and you get the most dip. And then when the faint star goes behind Algol, behind the primary star, you get a little bit less light coming. So you get a minor dip in between. So every other. So you get a shallow and a deep, a shallow and deep. The shallow is not really easy to see visually, but you can definitely measure it photometrically or photoelectrically. So the period of the repetition, the amount of the drop, all of these sorts of things let us talk about the orbits of the stars, the size of those stars, and the mass of them, and all kinds of other things. So let me talk about seeing Algol for yourself in the sky. So Algol is sitting here. This is the sky. I'll just bring it down an hour. So this is the sky tonight at about 11 p.m. local time. So if you want to look to the east-northeast, you'll see the Great Square Pegasus sitting up here to the upper right, and you've got the W of Cassiopeia. Cassiopeia, you've got the bright star Murphak, and then Murphak of star loop down this way, and then a kind of another arm of stars that run down here, and Algol is the star here. So look for Murphak, and the next brightest star you see sitting to the lower right here, and the distance of that is about a fist diameter, so almost a fist diameter to the lower right of Algol. Lower right of Murphak is Algol. Now here's the trick. So you can just do this with your eyes. When Algol is at its normal brightness of around 2.12, it's as bright as Almach, the star in under up here. Standing there, you can say, okay, there's Murphak, there's Algol, there's Almach. Do these two look like they're the same? Then it must be in its standard state. When it's at its minima, though, it's much closer in brightness to the star Gorgonia Tertia, not quite the same as that, but similar. And it's almost exactly as bright star triangle called Mathala, Alpha Triangularum. And so you can take Almach, Mathala, and Algol, and you can instantly sort of stand there and judge where it is in the brightness cycle. All right, so now if you want to observe Algol for yourself, it's one of these sort of things that you do of an evening or of an early morning if you want to do it that way. So you need 5 hours of time. You can either watch it dim or you can start with it. Not much fun, just looking when it's bright or just looking when it's dim. The trick is to get that range. So you want that 5 hour difference. The most convenient time of the year to do it is kind of starting around October, when Algol is just, climbing the eastern sky after dusk. And then 5 hours later, it's sort of sitting kind of overhead. So that's a great thing you're doing. If you're out stargazing, take a few minutes to look at Algol early in the evening, and then, set an alarm to make sure you check back with it later. So what I've got here is, oh, by the way, you can find the minimum of Algol on the monthly pages in the Observer's Handbook. So Samantha wants to hold up her handbook. So I can do it too.
It's the first time I don't have it with me because I packed it for camping. It's still in my bag.
Where is it here?
So Chris will show you. I apologize.
Goodness, where did they go? Here we go.
Should be in the back, right?
This year it's page for the month of October. And if you look down the right-hand page, you'll see every now and again minima of Algol, which are every 2 hours, 2 days, 12 hours, and 49 minutes. Now, there's one little sort of trick about this, and that is that not all sources are infallible. And it turned out that there was a bug in the minima of Algol for the Observer's Handbook for 2022. I know that the reviewers are dead set on making it perfect. The two ones in the printed version are wrong. So what you do is you can get the correct ones by going on to the updates. So there's an update page for the Observer's Handbook, and Samantha can put it in the chat if you want to do that. And the corrected minimum of Algol. So I'm
And
actually gonna.
We are gonna have the new Observer's Handbooks coming out in the next couple months, so you only need to do the update for a little bit.
So can I don't know if I can paste a paragraph. Can I paste a paragraph into the chat? Let me try this.
You should be able to.
I'm gonna do this.
What page did you say the variable stars was on again? We missed it.
The minimum alcohol?
Yeah.
One for October, it's 117. For September, it's 50. Let's try this. Let's happen. Do this.
Gonna steal your screen just to show people what it looks. So it's the one where we go month by month, right?
Yeah.
So I'm just gonna stop your screen sharing and steal it because I have behind the scenes. So yeah, it's on 115 on your Observer's Handbook. And you'll see, there we go, right at the bottom, Algol at a minimum, Algol. And then this guy for October, it's the one right after.
So just leave those out for a second. Let's just look at this for a minute. So when you're using the Observer's, what you look at, the first on the left is the date. So a day of the week and the day of the, you've got the hour and minute universal time, and then the description of the event. So you need to correct the time to your local time zone. And for example, in Halifax, I guess that's 3 hours. Toronto, it's 4 hours. Winnipeg, 5 hours. Victoria, Vancouver would be 7 hours, right? Subtract those number of hours from the Observer's Handbook. That's now. Once we end daylight savings time on, when's that? The November 6th, and you've got to subtract even an extra hour. So instead of subtracting 4 hours for Toronto right now, we subtract 5 after November 6th. So what a list of Algol, corrected ones, for the most of October. And you've got your date, you've got your universal time, and then I put some notes beside them. Maybe copy with a note, something like that. But I did examples of where you. So if I could come back to sharing.
Yep. For those of you who want to go back and check this again, you have your Observer's Handbook, but I'm also going to be putting it into the description box of the YouTube video if you need to go back a little bit later.
All right, so let's simulate a couple of these.
Your screen's just loading right now.
Oh, okay.
I will find that link for the errata for the Observer's Handbook. But as I said, unless just use what Chris said, and then next year it'll be all correct. Hopefully.
Okay. So what I did is I've just popped myself into Halifax. So Halifax, it's universal time minus 3 hours. And on October the 10th, I'm just going to advance to October the 10th at, I'm going to go 23:56. So this is the universal time. I'm going to subtract 3 hours. 1, 2, 3. So on October 10th at about 9 p.m. local time in Halifax, Algol will be shining over the northeast horizon, and it'll be a minima. It'll be faint. And then what you do is you can wait 5 hours. So 1, 2, 3, 4, 5 as it climbs the sky. And by the time it gets nearly overhead at about 2 a.m., it'll be back to its normal brightness. So that's one example of doing it. Then there's a few of them that are happening in the daytime for Canada. But of course, you know, international readers of the Observer's Handbook can use the minima that work for their local time zones. Let's do a Winnipeg one. So I'm going to switch to Winnipeg. Here we go. So in Winnipeg, I said on Saturday, October 22nd, at, so 11:12 UT. So I'm going to go 11:12, and I'm going to subtract hours, right? 1, 2, 3, 4, 5. So you're at morning sky here, unfortunately. Here's Perseus, here's Algol. So if you go now, so Algol will be at its minimum at 6 in the morning, which means if you want to see it fade, you've got to wind back 5 hours. 1, 2, 3, 4, 5. So you could, in theory, start watching about 1 o'clock in the morning, and then it's minimum. So that's a great one. I recommend it. Let's do Victoria. I've got a nice one for Victoria here. Victoria, Canada. Where's that? Here we go. Okay. So Victoria, Canada. Let's see. On the 25th of October, universal time is 8:01. And Victoria's 7 hours back. So 1, 2, 3, 4, 5, 6, 7. So Algol, let's go back into the eastern sky here. Here we go. So Algol is sitting up here high in the sky. So you can watch it fade. It'll be at its minimum at 1 a.m. So if you wind back 5 hours, 1, 2, 3, 4, 5, then it means you could start at 8 p.m. on October 24th and watch Algol fade over the next 5 hours. So that's a neat one. And so you can see, you can play this trick where you can kind of look at minima, convert to your local time zone, and figure out whether it will work for you or not. It's really fun to do, and it's easy for anybody to do. You don't need a telescope, don't need binoculars. You can just stand there on a clear night and look up and compare them. Let's go back to my home. About 9% of the variable stars are this type, eclipsing binary type. They vary, most of them vary by a magnitude or so over a few days. I think the minimum is a tenth of a day, and the maximum is 9,800 days for an extreme case. The star V342 Aquili, it varies by 3.4 magnitude every 3.39 days. So I'm not sure if I have this in my list, but that'll be, here we go, let's go over to Aquila. Let's see if we can find that one. V342, oops, AQL. So that's in the kind of upper wing of the eagle. You can see it's not a naked eye star, so it's really a binocular star in this case, or it may be a telescope target. How you can create finder charts to compare the brightness of the variable star with the neighboring stars, both for binoculars and for telescopes, in 2 weeks when we come back. Now, so that's a case where you saw the Algol's companion orbiting it, nice and neat. But eclipsing binary star systems come in a variety of flavors, a group according to how far apart the two partners are. So if they're completely separate, they're detached. They're called detached eclipsing binary stars. If they're close enough for each other for one or the other stars to be within the other partner's Roche limit to get pulled apart, then those are called semi-detached. And you can even have pairs of binary stars where they're so close that they're practically in contact with each other. They're sharing mass. So the semi-detached types include, which are a little bit rare, include V393 Scorpii, which I'm not going to show, and Shelliac, which I will show. Shelliac. Here we go. So Shelliac is part of Laura. So we'll go back to tonight, and I'll show you what it looks like tonight. clear where you are tonight, you can head on up, look at Sheliak. So Vega, then you've got the parallelogram of stars below Vega or beside Vega, depending on your orientation. And Sheliak is the sort of southwestern corner of the parallelogram. And it varies, as you can see here from Stellarium, it varies from 3.2 to 4.36 over 12.91 days.
Oh, we've lost you, Chris.
There's another star called W.
Oh,
testing.
sorry, we just lost you there, Chris.
Am I back again now?
You're back again now.
Okay.
We missed, you were giving us the numbers and then you stopped. You cut out.
Did you hear me say?
Oh.
Okay. Am I going again?
Yeah.
What to do about that? I'll just go a little bit slower and hopefully you can pick up what I'm saying.
I'm going to try to turn off your video to see if that helps, just in case.
Oh, yeah, I can do that.
Okay.
All right, let's see if that helps at all. So the star W Ursa Majori, which actually sits below the chest of the Big Bear, it's actually one of these binaries where they're in contact with one another. Okay, just back to Sheliak for a minute here. So giving people an observing challenge or observing homework to Sheliak. So Sheliak or Beta Lyrae, it changes from magnitude 3.2 to 4.4, which is about 3 times brighter or 3 times fainter to 4.4 over 12.9 days, as you can see down here. It's a contact eclipsing binary. The stars are 3 solar masses and 13 solar masses. So you can see there's about a factor of 4 size difference between the two partners. The illumination is about 92 degrees. So it's very, very close to edge on to the Earth. I'll show you the light curve.
I've also shared the light curve in the chat for anybody who wants to pull it up on their own screen while Chris is loading.
Yeah. So here's the light curve for Sheliak. And you can see that it's much less, because the stars are much closer together and they're not so distinct, you don't get as much of the off time as opposed to the dip time. It's much more of a sinusoidal. The peak and the minor peak insight. So when Sheliak is at its dimmest, let me just zoom in a little bit here. This is a great one to do with binoculars. Sheliak is dimmest. Okay, it's the same as across the box, across the way. When it's at its maximum, it's the same as Sulafat. So these 3 stars are your quick and easy observation of the variability of Sheliak. And what you can do is we're marking on the magnitudes of the 2 stars and deciding whether it's the same or in between. You would estimate the brightness of Sheliak and find out where it is in it. Let's see. I'll show you the light curve for the one at Ursa Major. And look at that. The stars are basically, it's basically like I don't know, like an hourglass just rotating in space. So you get the minima are almost all the same size. So you can tell by looking at the shape of the curve which kind of eclipsing binary it is, whether you get the gap in between or whether it's more sinusoidal. Now, rotating stars, so the star itself, if they have, let's say, major sunspots or non-uniform spheres, stars like BY Draconis, Barnard star, 61 Cygni. 61 Cygni is, let's see, is it on here? That's a good one. 61 Cygni. 61 Cygni is up here near the wing of Cygnus. It's a nice binary double star named Bessel star, but the A star is a variable star just because when it rotates, it varies in brightness. It varies in brightness because they're not spherical. They're kind of a wobbly shape, and when they show their oblong face to us, they're brighter. And when they show their end on to us, they're dimmer. And one of those is the star in the North American Nebula called V1794 Cygni. So this one sits here in between the North American Nebula and the Pelican Nebula in Cygnus. It's a pretty bright star, magnitude 7.2. So it has it's a not round star. So those are the various main types of the sort of extrinsic stars, except for one category, which is planet its light, and that's I'm going to let Samantha talk about.
Okay, so I'm going to take over. The one Chris would like me to talk about is the exoplanet, which causes variation in stars, and that is because I actually helped develop and work on a program with high school classrooms to discover exoplanets. I'm going to share my screen and show you all. So there's multiple ways, so it's loading, how exoplanets can vary stars. Chris mentioned right at the beginning, I'm just throwing this in here, it can vary the color. So as the star moves away and towards us, because they both are, when the exoplanet is orbiting the star, it kind of tugs it and moves it back and forth. That can shift the color. Won't go too much in that. But the main reason and how we found most of our exoplanets is just purely by measuring the amount of light or photons coming from the star. And when it dips, based on how the curve looks, we can tell there's an exoplanet that blocks some of that light out. So as you can see here in this example, there's an exoplanet orbiting the star. And there's a little chart on the bottom here. So we have our baseline, but as it goes in front, when the exoplanet goes between the star and us, it starts to block out some of the star's light, and we get that dip and it goes back up. Now this can take place over a very long period of time, or an hour, couple hours. There's tons that you can measure just in one night. You can also, depending on how the curve looks or how much it dips and in light and how that changes, you can tell the size of the planet, so the amount of light actually blocking, and how many planets. So if you get some weird dips and change in light brightness coming from the star, you have multiple exoplanets, as you can see in this third example here. So this is the transit method, and it's the most popular method for detecting an exoplanet. And you see it causes variable stars. They've detected, I think, almost 5,000 stars. And a Canadian was one of the first people to use this method. I'm going to also share, as we were saying, and I don't think Chris knows about this either, we do a lot of measuring variable stars on our own rastrobotic telescope, as well as measuring exoplanets. And we do this by taking images, and you can do this if you have any decent astrophotography setup. You just take an image in black and white multiple times over the night. I will share my screen here. And then you can use an open source software called AstroImageJ and use a technique called aperture photometry. And you can just measure how the star's brightness changes compared to standard stars that don't change. So this is an example of us detecting HAT P16b transit. So as you can see here, this are 4 other stars that we've measured it against has not changed their brightness, but this one has changed its brightness over that night. And this is because an exoplanet transited in front of it. So I'm going to do a little plug for RASC Outreach here. If you have a classroom or a group of students who are interested in exploring exoplanets, we offer it for free for Canadian educators. And eduscope.ras.ca. You can sign up for the program. You can look through your own telescope with your students and they can explore this area themselves. We've also launched, as of yesterday, an astrophotography program. And for maybe use not in education, we are working on, with the science team on the robotic telescope, a variable stars course that you can take with us and learn how to detect and measure variable stars with your own telescope. One more thing I am going to put in is a link in the chat to amateur astronomers, Lori and Kimberly Sibbald, who use their astrophotography setup to actually measure these exoplanets. And it's something you might already have at home, and you can turn it into observing variable stars or confirming exoplanets. Chris messaged the TESS satellite survey. They call a lot for citizen scientists to back up test data. So TESS takes data, and then they want you to confirm those results by doing measurements yourself, so you can contribute to citizen science this way. So this is a really cool topic, variable stars, because it's a part of this astronomy science that you can do at home with your own setup. And
Yeah.
so yeah, I think that's.
I'm gonna dive in a lot more into the offerings of the AABSO next time, and they actually have web portal tools for processing light curves and things like that you can use as well. So we'll show all the various neat tools that they have for those that want to get more serious.
So we have a question too here I missed. Do you know what if Betelgeuse is a intrinsic or an extrinsic variable? I know people were shocked with the dramatic decrease recently.
Yeah, so I think in the case of Betelgeuse's strange and rapid dimming, which I saw, I was in Florida on a trip, and I was sitting in a restaurant looking up, and I thought, oh, Betelgeuse is dim. What's going on? It turned out a lot of people thought, oh, it's getting up, but I think it's turned out it's published a couple of phenomenon all happen to sync up to make it dim. So Betelgeuse itself pulsates, and we'll talk about pulsating variable stars next time. So when the star pulsates, it varies in brightness. They also think that perhaps something in its atmosphere, something opaque, may have rotated into place or in front of the star on a temporary basis. And so that the pulsation and the opaque material blocking the light all sort of combine, give the extra dramatic drop that we saw for a number of months. So I think it sits in both, would count in both families, extrinsic and intrinsic.
And there's one more, stellarium. Is there a setting or a specific checkbox in stellarium, like we can highlight Messiers? Can we just highlight specifically variable stars? Or is that something we debug the developers to do for us?
Okay, so let me see if I can make this work, and then I'll share my screen again. Okay, let's try this. In Stellarium, well, in Starry Night, I know you can do that. I'm not sure about Stellarium, but what I've opened up here is down here under F10, there's a tool called the Astronomical Calculations window. And if you go to What's Up Tonight, WUT, you might be able to categorize variable stars. Let's see if there is. Bright doubles, bright variable stars. If you do that, click on that, it'll go off and think about it. So it's looking up the variable stars that are available to me at my location in the evening up to magnitude 11.5, which is too much, and that's why it's thinking too hard. It's always a good idea to turn that number down to get fewer hits before you do a search like this. We'll give it another second. Just come back in a second, then I'll kill the program and restart it. But that's one way you can do it. Once this comes up, it'll come up. There it goes. Comes up with a list. Star name, magnitudes of the star, the rise and transit sign time, its elevation, and its set time. What you can do is you can simply pick a star. Let's say we pick the brightest. We can order these by magnitude. So if we pick Vega, it's counting, double click, and Stellarium will center that star for you. So Altair. So it's not telling us how much they vary. So it might be, they might technically vary, but not really as much as what we're talking about today, the ones that we think we'd like rascals to be able to go and observe themselves. But there's Algol. So yeah, you can use this tool. And again, if you crank this number down to say 9, you'll get a shorter list. So you can just get the brightest set. Cool. Any other questions before we go on to Messier minutes?
As you said, this is not all we have to talk about variable stars. We're going to be talking about intrinsic next week, as well as how we can plot variable stars and all that. Not next week, 2 weeks from now, next episode. So if you think of any questions in the meantime, keep them in your head and you can ask us next time. But I don't see any for now. So let's go on to Messier minutes. And this is our second last Messier minutes. So
third last. Yeah. Well, 2 more sets.
We don't have a lot left.
Yeah, we have 2 more sets to go, but short, not long lists. Okay, here we go. So let's bring up the sky tonight around 9 o'clock. I'm going to bring up the meridian, because as always, the objects are better to look at when they're highest in the sky, and that happens when they're due south or crossing the meridian. I'll just bring up some Messiers here. Go into deep sky and turn off everything but the Messiers. Oh, did I kill the program?
Looks like it's thinking here.
Stellarium might be thinking of dying, or it might be just.
While Stellarium is thinking, just a reminder, ras.ca/Messier-minutes. We have a comprehensive list as well as finder charts, and we will link just the specific clip of this episode where we talk about Messiers to that website if you want to go.
Goodness, I need to get my technology fixed for next time. I've got 2 weeks.
It's not liking you today.
All right. So where we're sitting right now is we're approaching third quarter moon. So the next 10 days or so will be great for looking at deep sky objects. Give it a few more nights, but then we're in a really good time. Put on my meridian, bring up my Messier objects here. Try this one more time. So what we're talking about tonight is the last of the summer Messiers. So we've already covered a lot of the Messiers that are down here near the teapot, which Samantha saw for herself the other day. And now we're going to be finishing up the summer ones before we migrate into the autumn ones. We started doing some autumn ones, so we've already covered some of them. So that's why we're getting close to the end of the list. Up first is Messier 55. Here's my Messier 55. This one is here we go, in 55. I'll get on my Messier numbers here. It actually culminates around 9:30 p.m. local time, this time of the year. So you want to sort of pay attention to the time and try to catch that around 9:30 p.m. If you leave it late in the evening, then it'll be sinking westward and it won't be as good a view. That's because it doesn't rise very high in the sky or climb very high in the sky for Canadian observers. It is relatively bright. It's a big summer gem. It's large and close, globular cluster. It's only 17,600 light years away. It can be seen in binoculars on a good night with a haze-free horizon. inside the telescope will work. But if you have a bigger telescope, then you can resolve the stars and the core and the halo around it. Just show you the view. This is the view with a 10 millimeter eyepiece and a 6-inch Dobsonian. I'll switch this to the Plossl that I've been using. Here's the 25 millimeter Plossl. So that's what it would look like in a 6-inch reflector with a 26 millimeter Plossl. To find it, you can. It doesn't really, it's kind of alone in the sky. So what I did is I said, take the handle of the teapot from Nunki to Namalsadira 2 and basically do 3 more jumps. So 1, 2, 3 in that direction, and that'll take you to it. So you can take that distance and then do 3 times that distance in the same direction, and that'll pick up the globular cluster. Let's see, when you're there, you want to look at its shape, its density profile, look to see if you notice any variety in the stars, and note that sort of thing. It's called the summer rose stars, its nickname. So that's M55. Next up is M29. M29 is way up here in Cygnus, very easy to find. So you've got your Northern Cross shape of Cygnus. There's Albireo here, Deneb, Saturn. M29 is just tucked beside the, just nestled in there in the bottom of the neck of the swan. So it's basically a thumb's width south of, or in sort of the crook between the neck and the lower wing of Saturn. Really looks good at around 100K. So here's the cluster at about 35K, but if we crank it up a little bit more to say 100, that's 150, somewhere in between 100, around 100K is best. And this is sitting in a very rich part of the sky, lots of star fields around it. The cluster is fairly loose. You can see it's kind of scattered, pretty small, not really visible that easily in binoculars. Good binoculars, you might pick it up. Certainly any size of a telescope, you'll have no trouble. It's nicknamed the cooling tower, arises from 2 chains of stars that kind of diverge. I don't know if you can see star, 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 star this way and star, star, star this way, almost like the shape of a nuclear power plant stack. When you're there, you want to note the star fields around it. You want to take a count or an estimate of the number of the main stars. Look for any stars that are a little bit unlike the others, and see what kind of a shape you see. Maybe you don't see a nuclear power plant. Maybe you see things. Next up, we've got the Ring Nebula, the world famous Ring Nebula in Lyra. Very easy to find. Just aim your telescope finder midway between Siliphat and Chelyabinsk and look for a little smoke ring, little ghostly gray smoke ring in the view. It's small, but it's bright. Its brightness is enough to be within reach of basically any telescope, even in the suburbs. But a bigger telescope will show it much nicer, obviously. If you have an oxygen 3 filter or a UHC filter, that'll brighten up its form. And if the conditions allow, the seeing conditions allow, crank up the magnification and look for the white dwarf star in the middle. That's the core of the star that exploded and produced the shell of gas. M56. M56 is also in there. Here we are. So M56 is a globular cluster, and M56 is possibly visible in good binoculars, certainly visible in any size of a telescope, and you'll need a large aperture to resolve the stars in the core, which you can see here in this view. It's located almost exactly between Siliphat and Albireo. So just park your finder in between those 2 stars. Finding it. It's very far away, 32,900 light years away. It's possibly a globular cluster that was captured by the Milky Way galaxy, maybe when the Omega Centauri dwarf galaxy was captured. Again, you want to look for the star density, the density profile, the star colors. And when you're there, pay attention to look out for this deep red star HR 7302 sitting, it'll share the field of view. I think it'll, if I do this, although, so that star is just on the edge of the field of view. Okay. That's M56. M57 is in Vulpecula. So M57. Here. Sorry, M27. M27 is the Dumbbell Nebula in Vulpecula. It's another summer gem, very large, kind of diffuse, but bright enough for most of us to use at our star parties, even in the suburbs. We can show people the dumbbell in our telescopes. I've seen reports that large binoculars can see the dumbbell nebula, but you've got to be in a very dark sky for that. But any telescope will do. The dumbbell. It's about 3 degrees northeast, or 3 degrees north of the star Gamma Sagittae. So if you find we looked at Sagittae at the start of the show here. This is Sham, and look for Gamma, and it's about 3 degrees from here. Or you can take a line from Sulfat. So draw the line from Sulfat. Again, you want to, if you have it, use an oxygen-free filter or a UHC filter to better show the shape of the nebula. Just bring up the eyepiece view here. And again, you want to look for what shape do you see, maybe sketch it for the white dwarf star. If you can pick that up, maybe you try using your averted vision to pick up some more of the details in it. All right, couple left. M71 is next. M71 is this globular cluster that's just tucked halfway along the arrow's shaft. That makes it very easy to see, just between Gamma Delta Sagittae. It's small in size. It's bright enough for binoculars in a dark sky. Any size telescope would be fine. Larger aperture telescope will better show the core. And you want to look for the rich star fields around it. Note its shape. You know, it's not as dense as some of the other globular clusters. It's only 13,000 light years away from us. So it's a real gem. That's the M71. Finally, we've got 2 more here. M39. Is at the back end of Cygnus. M39 is a very large but sparse open cluster. So you can see it, you know, barely stands out against the field around it. You can certainly pick it up in binoculars in a dark sky, any size of a telescope. Don't magnify it too much because it's quite big. They don't have really any bright stars to guide you to it, but it does sit halfway between Deneb and Alpha Centauri. So pick up Deneb and down to Alpha Centauri. It's on that line between those 2 stars. When you're here, when you've got it in view, you want to sort of estimate the number of stars you see, note for any patterns you see. It's only about 825 light years away, M39. And last up, we've got M75. M75 is, where are we here? Down here, again near the teapot. I let this one last, even though I recommend viewing M55 earlier in the evening. You've got a bit more time for M75 culminates, so you don't need to both. You can do them both at the same time if you want to. So this is the most easterly of the summertime Messier objects. So it was actually the last one in our 110 Things to See book. It's medium-sized, relatively faint. Let's see, you can hardly see any stars around it. As I zoom in, it's pretty small. You might see it in big binoculars on a good night, but definitely a larger aperture telescope will be needed to see it very, very well. Again, it's not near any bright stars per se. So what I did is I actually star hopped to it in the eyepiece by following patterns. I picked it up. But you could try doubling the line from El Nazl. So where's my El Nazl? You could come from here and see the teapot. It's sort of, if you think about crossing the teapot diagonally, so from El Nazl to Namal Sadira 2, and it's about twice that distance. That's another way you could try to find it. When you get there, though, if you do use those two stars, see they'll point to a spot a little bit below the cluster, so you just want to slew a little bit to the north. When you're there, just show you so it's really, really tiny. The core is very flat. In a regular telescope, but you can take a look for that, look at the density profile, note its shape, look for any unusual stars. It's a very far 67,500 light years away. And that's it. That's the last of the summer Messiers. We're done.
Oh, now it feels like summer's over. We can still
Soon.
look at them though.
Soon.
I will say, as a comment about the star hopping, I was worried when I was going out as a new observer doing big distances, but I found as long as I prefer to use something that I could recognize versus something that I wasn't quite sure about. The hardest part for me was to know that I actually had found the object. M13 for a while, I was looking for it and I kept on thinking I was going to see a lot of stars versus just a faint fuzzy, because I didn't connect that binoculars would just, I thought they would see more individual, like an open star cluster, but I didn't realize I'd never seen a globular through my binoculars before. So just some advice for when people are finding this. And if you do things like that, the teapot, to get to the last one Chris mentioned, just kind of be prepared for what you're looking at or how small it's going to be. And those big jumps do help, at least when as a new observer, if that makes sense.
Yeah, the other thing, depending on your telescope type. So for example, there are tools online where you can calculate the field of view provided by your telescope in particular eyepiece. So when you do that, you can actually dial in the field of view into your stellarium. So let me go to 1.5 degrees here. So I'm making a circle that matches the field of view in my favorite eyepiece, the one that gives me a nice healthy field of view. Now, you want to bear in mind that if your optics flip the view, you have to account for that. So if you're using a Newtonian reflector, like a Dobsonian telescope, then you can use the flip buttons to flip both. And now you're here. So bear in mind that if you say center the star Dabby in your view, what direction do I need to move the telescope to get to my target? Well, it's actually to the upper left because it flipped it around. So what you do is you kind of zoom and you say, well, okay, I think I see this little triangle and this little smile. So I'm going to take those and I'm going to put them on the other side of the circle. And then I say, oh, okay, I see this sort of flat Cassiopeia here. So I'm in where I need to be. I'm going to bring that down to the bottom of the field of view. And then, oh, there's a Y. I can see that Y. So I'm going to take that Y and I'm going to carry it down to the field of view. And you just do this a few more times. And it's nice if you've got something like a Stellarium app or a Sky Safari to help you to do this. If you get lost, just sort of go back and pick up your bearings again. So there's that Y I talked about. And say, okay, well, I recognize, from my star chart or my atlas, this star. So I'm going to bring it down. Let's see how many jumps. Oh, we're getting close. So put that near the field of view. Oh, here now there's a little sort of a mini Perseus shaped asteroid. need to go a little bit further and then you're there. And once you're here, then in your star atlas, you want to see, well, do I see this big triangle of stars and my object should be along one of the sides of the triangle? That's the sort of trick, the technique that you'd use. So it takes practice, but you can do it. It works.
Yes, it definitely does. And even just sitting here all the time by osmosis, you'll be surprised what you can pick up. I was sure surprised, as Chris said, I saw the teapot asterism for the first time. And I just looked in the general direction thinking I was going to have a hard time finding it, but it popped out at me because I had been listening to Chris talk and just being around and looking for that shape that I was finally able to identify it in the sky once I had the horizon to do it. So keep going, a little bit at a time. I'm still intimidated by Messier's, but I know I'll get there one day. So I hope you guys all have found this very helpful as well. We have no more questions. Somebody did ask, because we mentioned a couple times the YouTube channel and the Insider's Guide. I've thrown a link just to our page where we keep all our upcoming course dates. I just need to adjust it to add the new ones coming up. And a link, and on that page, we also have a link to our playlist, which is on YouTube with all the past Insider's Guide to the Galaxy episodes. We are well over 50 at this point. So you have many, many hours to look through. And that same page, you can also go to the Messier's. And thank you all for coming. Any last words, Chris?
Just keep looking up. We're getting into that time of year where we get fewer clear evenings. Once we get closer to October, it gets a little bit gray outside. So take advantage. I'm hoping to get advantage of this next moonless week so we can get our last.
Oh, yes. And we are now back to our regular schedule. We just saw a question once every 2 weeks. So we are going to have the next one on September 27th. And as I said, the schedule will be on the website. I will just be updating it now that we are in the fall. I guess we're not officially fall yet, but very close to being officially into the fall season. So,
yeah. So, yeah.
Thank you.
Clear sky.